In the first question, we are asked to use the inverse law to find the magnetic field at any point in the volume between the conductors. So we have the small conductor with radius a here. So for the question A, it asks any points in this diagram. So there's 4 points. The first one is just inside the conductor where R is less than A. And the second point is in this empty space. It's outside the conductor but inside this tube here. And the third one is just on this tube. And the last one is outside the tube. So in the first scenario, when R is less than A, by inverse law, we will have two equations. The magnetic field times the area is equal to current times mu zero. And also, when a current flow to this conductor, it will change. It will goes into the current times the radius of the point over and square over the radius of the conductor square. And when we plug this function into this equation, we'll have the I times the current I times the radius of the point, r squared just r squared times mu zero over the radius of the conductor times 2 pi r. This is the area. When we simplify this, we will have the answer. And for the second scenario, when R is greater than A but less than B, it's in this in this empty space, so the current will not be affected. The current will be just I, and just divide the area from both sides, will have the answer. For the third one is on this tube here, so the current will be affected, so the radius will be r squared minus b squared. So the radius of here b, we need to minus the empty space, also the conductor, so we just get this y's, and over the c minus b. Oh, this is y's. No, sorry, it's the point on this cube here to here. If this is r, so this over the whole y's will get the current. Then as this is the one before, we just plug this in and we will have the answer. When the radius is greater than c, it means it's outside of the tube, and there will be no current outside of this cube. So when the current is equal to 0, the magnetic field will be 0 too. For the second question, it asks the expression for the flux through a narrow strip of length L parallel to the axis of the y's dr at a distance r from the axis of the cable and lying in a plane containing the axis. So also, we based on the Faraday's equation, the flux equal to the magnetic field times the area. Because it's a strip, so the area will be just the length times y, and that's the answer. And for this one, it says integral expression from B, so we just and it's between the two conductors, So the two conductors are the small solid one and the tube. So between them it's the empty space. So we just integrate the equation before and put the range as A to B, and we'll get answer. For D, it says calculate the inductance per unit length L over the letter L for the table. So based on the equation, so L is equal to number of terms times the flux, because there's only one term, so N is equal to 1. And flux B we just got there, got from previous question. It would be the current times mu0 times the length, and ln b over a over 2 pi. We just plug this into this function and also divide by L, and we will get answer. It's mu0 times ln b over a over 2 pi. And for E, it's asked to calculate the energy stored in there. So the U is equal to the inductance times the current square over 2. It's easy, so we just plug this L over little l into here and divide L. Yeah, get rid of L, we'll find. So the answer will be it's the L times the current square, and there's over 2, so the 2 pi becomes 4 pi.